Good day. The talk estimating the probability of disparity in the absence of bias is a talk that I have given in both the regional and national meetings of the Casualty Actuarial Society. I am recording this in my house in case you are interested in the content of it but were not able to be in attendance those days. So without further ado, here we go. So, first of all, who am I? Well, I'm a consulting mathematician with EP Analytics Solutions. My formal training is in mathematics, in particular functional analysis and complex analysis, and I am an associate of the Casualty Actuarial Society. I've got 12 years of experience in data science, R&D, and predictive analytics, 2 years in operations and IT, and for the most part, almost all of my research focuses on the application of theoretical mathematics to data and actuarial science. With this talk, what I hope to do is to demonstrate a method to estimate the false positive rate of various measures of disparity. Along the way, this will allow us to bridge technical and colloquial meanings of the word random, and we will illustrate how to generate a multivariate mapping using geometric reasoning. On the personal side, what I am always attempting to do through the research is to create tools to swiftly build models which are precise and also explicable so that they might inform the action of the stakeholder. Okay, so now what's the impetus for this particular talk? Well, there's a few of them. Among other things, you can see in the popular press that in recent years much has been made of various disparities. And so here are two examples from US News and World Report, as well as CNN. The first having to do with the racial makeup of America's prison, and the second one having to do with the gender makeup of the C-suite. Now, you might just say that, well, look, the press is going for clicks and they'll write whatever they have to. And perhaps you're correct. But we should also check to see whether or not that same impetus, or rather that same curiosity, has presented itself among the public. And what you can observe if you go to Google Trends is they will tell you that a value of 100 is the peak popularity for a search term, and a value of 50 is where it's half as popular. And then if you apply that and look at things like, say, disparity, what you'll see between the years of 2005 and 2020 is a marked increase in interest for the term over those years. Even sharper is the Google searches for the word bias, which took place between those same years of 2005 and 2020. So apparently, it is not in fact limited only to the press. With respect to the Casualty Actuarial Society, part of our continuing education requires that we consider the topic of bias for at least one continuing credit hour a year. Okay, all well and good, but one of the difficulties you'll have with articles like the ones at CNN and US News and World Report is that they usually omit any sort of statistical discussion. And that's fine for journalists. They're not statisticians. But if you're an actuary, if you're a statistician, if you're a data scientist, you're going to want to dive into the topic a little bit more deeply. And so we're going to start off by talking about what do we even mean by disparity or bias? Well, when we say disparity, what we're going to mean here is it's a characteristic of a sample which is significantly different in a statistical sense from the population from which one is purportedly sampling. So an example would be if you have a coin, quarter say, you flip it 5 times, it comes up heads each time. That's only going to happen with probability 3.125%. And so you would say that seems significantly different, that sample, from the population from which you're purportedly sampling, which would be a fair coin. And then bias is when the population from which you are purportedly sampling is actually different than what you thought it was. And so with respect to the coin example, we would get the 5 heads and we would say, supposedly we were sampling from a population involving a fair coin, but I think that the coin might be weighted. I think it might be an unfair coin that comes up heads with probability much higher than 0.5. And so the observation of the disparity when it's sufficiently different from what we would expect would cause us to say, you know what, I have to reject the null hypothesis that I was sampling from this population from which I thought I was. So, of course, the question becomes, well, when does disparity imply bias? Okay, well, let's go through a couple of statistics 101 examples. So suppose that women are 50% of the population, so that's the population from which we're purportedly sampling, and a company has 100 employees. Well, you can ask, would it be a disparity if 49 of the employees were women? How about if one of the employees was a woman? Would that be a disparity? Well, how would you do this formally? Well, what we would say is, if the proportion of women in the sample is statistically significantly different from the purported population with a significance of, say, 0.05, again, you get to choose your own level of significance, we're going to declare it to be a disparity, and then we might go, that's a disparity, maybe there's some bias going on here. We would at least consider the possibility of bias. All right, well, again, because we're good statisticians, we know that when you are doing this kind of experiment, the random variable of interest is a binomial distribution with probability P equals 50%, and then N equals 100 because you're looking at 100, the company's got 100 employees. And what this means then is that the statistically significant region is 0 to 40 and combined with 60 to 100. So if your results end up in either of those intervals, you have a disparity. And so thus we would say, well, in the second case with just one woman, that's definitely a disparity. 49, it's like, no, that's fine. That's not in the significant region. Now, what becomes more difficult is when multiple variables are under consideration. So in the previous slide, we did the sex of the employee. But if you pay attention again in the popular press, you'll find often that there are multiple categorical variables that are under consideration. So a very common one you'll see in the press is race. And so here's an example of that. I believe this comes from Time. This is an article about President Obama, the hope and burden of being the first black leader in your field. Okay, so we're taking race into account. Again, much was made in 2020 when Kamala Harris was declared to be the vice presidential running mate of Joe Biden. Why? Because she was present tense, a black woman. Again, much was made of Karine Jean-Pierre when she became White House press secretary. Why? Because she was black, because she was a woman, and because she is, present tense, is a lesbian. So that's three categorical variables at once. And now this makes the question of bias much more difficult. Because when you are doing this kind of analysis, formally what you're doing with any categorical variable with, say, more than two values is that forms what we could call a multinomial distribution. And however, in the press, again, in public discourse, a lot of disparity is discussed in univariate terms. And so I did my best to extract what I think is the rule from the different articles that you'll see. In the implicit rule for detection of disparity seems to be that a sample taken from this multinomial distribution, if it's the case that a single variable, perhaps formed from considering intersecting or interacting multiple categorical variables, is examined for extreme values, if one of those values comes up discordant with respect to the underlying population, then disparity is declared. Now, this is the rule rather for disparity that I'm intuiting from public discourse in the press. For the methods presented in this presentation, you can take whatever value, or rather definition of disparity that you like. So to sort of illustrate how this could work in practice, consider again the company, we got 100 employees. And, hey, look, maybe it's the case that there is no statistically significant difference between the percentage of females and the overall population and blacks in the overall population. So we go, okay, we're good. Great. But perhaps it is the case that there is a statistically significant difference between the percentage of gays in the overall population. And maybe while it's the case that there is no statistically significant difference between females in the overall population and blacks in the overall population, there is a statistically significant difference between the percentage of black women in the overall population. And so because of these three disparities we found, two disparities, gays and black women, we would say, oh, two disparities. There might be bias going on here. Well, what you can obviously see from this is that when you increase the number of variables and the number of combinations of those variables to examine for disparity, you're going to increase the probability of finding a statistically significant difference if you test all of these different combinations, this variable and that variable and these combinations and those combinations with, say, the typical 0.05% test. But now the question is, by how much? So it's a very simple question to state, which is clearly the more places you look for trouble, the higher the probability you're going to find it. But by how much? Does it double if you double the number of variables? Does it go up at a logarithmic rate? Who knows? So the question is, by how much? And this is where we sort of depart from what this talk is ostensibly about, disparity and bias, to what it's actually about, which is the multiple comparisons problem. So this was known to Tukey at least as early as, I think it's 1953, this problem of doing statistical tests, which is that, yeah, if you do one statistical test, you're fine, but if you're going to do like 100 of them, well, then you need to in some way be much more judicious in what you're going to take as statistically significant. Otherwise, you're almost guaranteed to find it. The purpose of this presentation is to help us figure out by how much. So to illustrate this, let's take pretty much the simplest example we can involving two variables. We'll take two variables, x and y, and they each take two values. And the purpose of these next few slides is to illustrate the difficulty of actually calculating the probability of disparity. So here we go. What we're going to do is we're going to define there to be a disparity if a number, so we got this table, we got two variables with two values each. We're going to sample from this table 100 times, and we're going to define there to be a disparity if a number is selected outside of the 5% confidence interval for any cell in the table or for any value of each variable. And then we're going to try to figure out what is the probability that a disparity will occur. Now, you'll probably say, well, Ian, doesn't that depend on the probabilities for each cell in the table? The answer is yes, of course. So, to aid us in our quest, we started off with the simplest table structure we could with multiple variables. We'll start off with the simplest table we can imagine for these multiple variables, which is just everybody gets the same probability. Okay, and then we'll just let these C variables here, these will be our counts for each cell from the sample. And so in order for there to not be a disparity, what would have to happen? Well, taking each variable and each value of each variable one at a time, we see that the sums of our counts have to be between 40 and 60. So what do I mean? What I mean is that when we look at x taking the value 1, the count of x taking the value 1 and y taking the value 1 and x taking the value 1 and y taking the value 2, so this row here, the counts associated to these guys have to be between 40 and 60. Similarly, the counts for these guys have to be between 40 and 60. The counts for the columns have to be between 40 and 60. And so that's just taking each value of each variable individually. And then each cell, so the count in each individual cell, has to be between 17 and 34. And so we have to somehow count all the number of ways, all vectors of 4 integers such that these conditions hold and they sum to 100. Now, as you might imagine, this is somewhat difficult, so, okay, we give ourselves a little bit of a... We try to make the problem a little bit easier, and we go, okay, well, what if we fixed the count of C11? So that's the number of counts we have where X is 1 and Y is 1. And we say, okay, we know that's got to be at least 17. What if it is 17? Okay, well, now we're kind of in good shape because although there's 4 count variables here, we know they have to sum to 100, so we have 3 degrees of freedom. We just eliminated one of those degrees of freedom by saying, let this guy be 17. So now we just have 2 things about which to worry. And so, assuming that C11 is 17, we're able to deduce a few other pieces of information, such as this and this. And we go, great. Now we have a nice geometric expression because, again, we have only 2 degrees of freedom, so we can plot that in the plane. And that means that we simply have to count the number of integer pairs in here. And that will allow us to figure out the number of different values for these variables here when C11 is 17. Okay, but then we have to do it when C11 is 18, and then 19, and then 20, up to 34. So obviously this is going to be a big pain, and moreover, that this is for a single table and a single set of probabilities. So this hardly seems tractable. Again, you might try an inclusion-exclusion principle here. So you count the number of times each one of the criteria hold individually, and then you subtract out where they hold 2 at a time, and then you add back in where they hold 3 at a time. That's another route you could try. You could try generating functions. You could take this polynomial and raise it to the 100th power, and then sum the coefficients on the terms whose exponents satisfy the inequalities and divide that by 4 to the 100th power. That'd be another way to do it. Again, as I said at the start of this, the whole point of these slides is simply to illustrate to you what a pain this is and how difficult it is. So, what are we going to do? Well, we're going to do what we often do in math when no closed form solution presents itself. We're going to attempt to solve this problem numerically. And the way you do this is you make a very simple observation, which is that disparity itself is a Bernoulli random variable. It's 1 or 0. It's binary. It's on, it's off. Either there was a disparity, whatever your definition. Recall I said earlier that you can take whatever you want as your definition. Either there's a disparity or there's not. So it's a Bernoulli random variable, and that's very useful. And it's very useful when we remember Chebyshev's inequality. What Chebyshev's inequality allows us to do is it allows us to figure out the probability that our sample mean is far away from the actual mean. So this P here is the actual probability of disparity, and this X bar N is going to be the sample mean, where we take a sample of 100 from the table, look for disparity, take a sample of 100 from the table, look for disparity, take a sample of 100 from the table, look for the disparity, and so on. And then we take the sample average. We look at the average number of times that there is a disparity. And so Bernoulli's inequality allows us to say, I think that the sample mean is this close to the actual mean with some probability. And so one of the nice things about Bernoulli random variables is that their standard deviation maxes out at 1/2. So that's why we get to make this inequality here. And now right here, we've got a very nice formula, because we're able to bound the probability that our sample mean gets too far away from the real one purely in terms of the number of times that we perform this experiment. Once you've specified your epsilon, once you've specified how tight of a control you want, we can just calculate what we want n to be based on the probability that we're trying to obtain. So it's very simple numerically. What we're going to do is we're going to sample from this table. We're going to draw a sample of size 100 from this table and look for a disparity 5 million times. And when we do that, this will allow us to estimate the probability within 0.001 of the true one with probability 0.95. And when you do that, what you find out is, looking at each of the individual variables, their values one at a time, at least one of them is going to be off roughly 7% of the time. And so that means that either x equals 1 is too big or too small, x equals 2 is too big or too small, y equals 1 is too big or too small, y equals 2 is too big or too small. Looking at it two variables at a time, looking at their intersection or their interaction, however you want to say it, roughly 13% of the time, one of the counts for one of these cells is going to show a disparity. It's either going to be too big or too small. And then overall, you're going to see a disparity about 15.5% of the time. So, there you go. Problem solved for a single table. Now, you might be saying to yourself, as you mentioned earlier, well, surely the probability of disparity changes with each table, doesn't it? And the answer is yeah, of course it does. So here's a different probability table, same structure, two variables taking two values each. We're going to draw samples of size 100 from the table, but now we've got different probabilities here. And we're going to do the exact same thing. We're going to grab samples of size 100 from this table. We're going to look for disparity, and we're going to do that 5 million times. And that will allow us to estimate the probability at the third decimal place with probability 0.95. And when you do that, what you see is that about 7.8% of the time, one of the values of one of the variables is going to be out of whack. It's going to be too high. It's going to be too small. If you're looking at the intersection of the two variables, one of these counts in one of these cells is going to be too high or too small about 10.5%, 11% of the time. And then the overall probability of disparity is about 12% for this particular table. So, in one sense, we're in good shape because although coming up with a closed form calculation for the probability of disparity for a fixed table is it's not tractable, there is no closed form for it, or if there is, it's very complicated. That's fine. We can use simulation and we can just hit this problem numerically. The difficulty that's demonstrated and still confronts us, though, is that for two different probability tables with the same structure, same number of variables, each variable taking different, the same number of values, and a fixed sample size, once you change the probabilities in each of the cells, you're going to get different false positive rates for bias, right? Is that you're going to see disparity even though we were faithfully selecting, grabbing samples from that table. And so the question then remains, how is one able to estimate the probability of a false positive as such, like without respect to the underlying probabilities? How is one able to estimate the probability of a false positive without referencing the underlying multivariate distribution? And is there a universal statement that we can make about disparity implying bias as such? So, let us proceed to the sampling scheme. So here's what we're going to do. Here's what we've observed. We know that given a table structure and a sample size, how often we see a disparity changes with the underlying probabilities in the table. So, what we're going to do is we are going to average the probability of disparity over all of the tables of a fixed size. So thus far we have seen 2x2 probability tables, and there's an infinite number of them. Each one of them has their own probability of disparity in the absence of bias. Again, we're faithfully sampling from the underlying table. We're observing bias. Each one of them has their own probability of observing bias. we are going to average over all of those tables. Now, it might not be immediately obvious what it means to average over the space of tables, because that would imply that there is some sort of natural measure on the set of probability tables, that there's a way to average over them. So what does that even mean? Well, consider the following. Think about what goes into the construction of a probability table. And again, for illustrative purposes, let's think about, sort of the simplest of examples here. It's a table with 3 values. So what do we have to do here? Well, we know that that the sum of the probabilities has to equal 1. Moreover, we know it's relatively uninteresting if any one of those values is either 0 or 1. Because if they're 0, then we might as well just be considering a table with 2 entries instead of 3. And if one of them is 1, then there's nothing probabilistic about it at all. It's simply certainty. Thus, we see that each of the individual cells has to be between 0 and 1 exclusive, and they have to sum to 1. Which means although there's 3 choices to make, really, there's only 2 choices to make. So we have to somehow judiciously select x1 and x2 such that they are between 0 and 1 exclusive, and their sum is less than 1. Now that first part is really easy. So generation of uniform random numbers is the simplest thing in the world. It's very easy to get numbers that are between 0 and 1 exclusive. That's the basis of all number generation in every computer. The more difficult thing is, once you've got them, how do you map them to an area in R2 where they sum to something less than 1? And so that's what we want to do, is we want to sample from the unit square and then somehow perform some sort of transformation on them such that they become that their sum becomes less than 1. Again, consider a table with 4 cells in it. What do we have to do here? Same answer. You have to have 4 numbers between 0 and 1 exclusive such that their sum adds to 1. And again, it's very easy to find a triple of numbers who are between 0 and 1 exclusive. The somewhat more difficult part is to map them to the area of the unit cube, which lies beneath the plane where the sum of the entries in the plane equal 1. But if somehow you can do that, then you'll be in good shape, because then you'll have 3 numbers between 0 and 1 exclusive, and because their sum is less than 1, x4 will simply be the difference between their sum and 1. So, it's actually easier than you think, or rather might have thought, to generate probability tables. Generation of uniform random numbers is easy. This mapping here that takes those triples, that takes those pairs, in general takes those vectors, and transforms them to be something whose components are still in the hypercube, but sum to something less than 1, that's the work that we have to do. But at least we've narrowed it down. So before describing that map, before describing that transformation, let's just put some definitions in place. We're going to refer to H as the hypercube. So this would be the unit interval. On the real line, it's the unit square in the plane, it's the unit cube in 3 space, and so on, in the higher dimensions. We're going to let T be the part of the hypercube where the sum of the components of the vectors sum to something less than 1. So again, in R2, that's the triangle, which is a subset of the unit square. In R3, that's the part of the cube which lies beneath the plane that slices through it, where everything in the plane sums to 1. Let's just pretend, for the time being, that we have a map that takes the cube, takes the hypercube, and maps it into T, where T is short for table space. And then our job is really easy. If we had such a map, if we had such a transformation, what we could do is we could just randomly sample from the hypercube. We could map that sample into the table space. That map creates a table with n+1 cells. So recall that when we had to create a table of 3 entries, we started in R2. When we needed a table with 4 entries, we started in R3. So if we are starting in Rn, we get a table of n+1 entries. So we sample from the hypercube, we map to the table space. This gives us a table with n+1 cells. Then we can sample from that table. We can sample from that table. We can look and see whether or not a disparity occurred. And then we do that 5 million times. Pretty straightforward. Okay, I'd like to now take an intermission and talk about connecting the intuition and precision regarding random. What does it mean for something to be random? Now you're going to get roughly 2 answers to this. One is the man on the street. If you select someone at random and say, what does it mean for something to be random? They're going to give you an answer that's something like, anything can happen. Anything can happen. A volcano can erupt beneath my feet. Candy canes fall from the sky. You know, I win a Lamborghini in a lottery, but then it explodes. Like, anything can happen. But now if you go to the academy and you say, what does it mean for something to be random? They will say, which random? We can't just have anything go on. Which random do you mean? Do you mean normally distributed? Do you mean uniformly distributed? Do you mean Poisson? We need some structure to our randomness, my friend. So it would seem that in the academy, random isn't anything can happen. We gotta rein that in a little bit. Well, with what I'm proposing here, we have a little bit of a connection. And the connection is that anything can happen when you sample randomly from the hypercube, because it's uniform random numbers. Anything can happen. But once you have selected that anything, that gives rise to a probability table which does in fact have an underlying structure. Any table can be selected, but once that table is selected, then we have an associated structure to which we may appeal. Okay, so now of course the question is, how do we create that transformation? How do we create that mapping? And the title of this section perhaps gives the game away a little bit too much, but I think it's useful to understand how to do things poorly before seeing how to do them well. So again, H is our hypercube, T is the table space, and we are looking for some way, any way, to map or to transform the hypercube into the table space. So, what's the easiest way to generate a vector of values where each value in there, each component is between 0 and 1 exclusive, and the sum of the components of the vector sum to something less than 1? Well, before you can pick a vector, you got to pick the first component of the vector. And so, okay, I want it to be between 0 and 1 exclusive. And, well, if it's between 0 and 1 exclusive, certainly it doesn't sum to 1. So I will simply just generate a random number between 0 and 1, and I'll take that as my first component. Gets the job done. So far, nothing's violated. Okay, cool. Well, that was easy enough. How about component number 2? Well, I've selected my number between 0 and 1. So how much probability do I have left? I can't just pick another random number between 0 and 1 because now their sum might be too great. How much probability is left over? Well, 1 minus the first number I selected. Okay, well, then why don't I do this? I'll select a second random number. Now again, u2 plus u1 might be bigger than 1. But what I can do is I can use that second random number between 0 and 1, and I'm going to use that to scale the amount of probability that remains. So the amount of probability that remains is 1 minus x1. I'm going to multiply that by u2, and then I'm going to do a little bit of algebra, and I realize, okay, the second component in my vector in the table space is u2 times 1 minus u1. Okay, good. How much probability is left over? Well, 1 minus x1 minus x2. Okay, I'm going to do roughly the same thing. I'm going to generate a uniform random number. I'm going to use it to scale the amount of probability left over. I'm going to play around with some algebra, and I'm going to realize that this third component in my vector in the table space is u3 times 1 minus u1 times 1 minus u2. I'm going to compare that to u2, and I'm going to go, I think I see a pattern here. And so in general, the pattern is the first component is just some random number, and then the subsequent components are you take the product of 1 minus all of the random numbers you've selected previously, and then multiply that by the number you're selecting now. And you should be in good shape, because each one of these things is between 0 and 1 exclusive, and they sum to less than 1 by design. So we're in good shape. We've got a way to map the hypercube into the table space. Good for us. And here it is. And so now we want to check a few things, right? So we go, well, okay, look. Is the function bijective? We used that word earlier. What does bijective mean? It means that unique points in the hypercube go to unique tables in the table space. We don't want 2 points going to the same table. We don't want to double count. So we want to make sure that it's 1-to-1, or injective is the word for it. We want to make sure that it's what's known as onto, that for every table in the table space, there's some point in the hypercube that goes to that table. That'd be very nice. That's what's also known as surjectivity. So 1-to-1, injective, onto, surjective. We're not double counting, and every table has a point in the hypercube that gets mapped to it. And because it's a multivariate polynomial, multivariate polynomials are continuous, and we go, this is just great. This is great. We've got a continuous bijective function. It's continuous both ways. You got to do a little bit of work, but you can show that. It's not troubling. Just a basic proof by induction. We're in good shape. So we should be good, right? Well, here's the thing. This was the original mapping. This was the original transformation I was proposing. And so I dutifully programmed it into my computer and began using it to generate probability tables, sampling from those probability tables, and then recording whether or not disparity occurred. Upon doing so, what became clear was that I seemed to keep picking tables, not all the time, but for the most part, I seem to keep picking tables where the first component is bigger than all the other components in that table. The value, the probability in the first cell is bigger than all of the other probabilities in all of the other cells. And so what that would seem to indicate is that the function does not map regions of the hypercube to regions in the table space that have the same relative volume geometrically. And then to make this more explicit, once you've realized that's going on, you can quickly realize why it's going on. Well, because among other things, the probability that the first component in the table, the first cell in the table, has a probability of 0.5 or more, I'm sorry, that the probability that X is larger than all others is clearly bigger than 0.5. Well, why? Well, because the first cell is simply a uniform random number. And half of the time, uniform random numbers are bigger than 0.5. And so that's just for the times that x1 is bigger than 0.5. But x can still be bigger than the probability in the first cell. X1 can still be bigger than all the other numbers, even if it's not 0.5, even if it's smaller than 0.5. So this is no good. We somehow accidentally are biasing our probability table construction such that the first component is always biggest. What a bummer. So this whole thing's a bust. So how do we do this? Well, what this made us realize is that it's desired that not only are regions of H equally likely, which they are because it's a uniform random number generator, we also want regions of the table space to be be equally likely. Okay, so that's what it is verbally. But what is that mathematically? Well, what we're going to do is I'm going to write G as the inverse transformation. So F takes the hypercube into the table space. G takes the table space into the hypercube. This is going backwards. You might wonder why I'm doing it that way, but there's a reason for it. And we say to ourselves, okay, well, that's verbally what we want. How do we write this down mathematically? And what we're saying is, well, if you take a region in the table space, which we'll call E right here, if you take a region in the table space and map it back into the hypercube and say, what's the measure of that? Well, that's measure of G of E. M is Lebesgue measure, G of E. We want that measure to be equal to the relative measure in the table space. What do I mean by relative measure? I mean the Lebesgue measure of the region divided by the measure of the whole table space. Well, what's the measure of the whole table space, M of t here? Well, that's 1 over n factorial. So recall that, for instance, in 2 space, in R2, H is the unit square, and T is the triangle. What's the area of the triangle? It's 1/2. With some work, you can see that the volume of the cube in R3 is, of course, 1. The volume of the area of the portion of the cube that lies beneath the plane, where the sum of the components of the vectors in the plane equal 1, is 1/6, or 3 factorial. And so what we're asking then is we want this equation to hold for all regions in T. And again, like I said, I've written it in this extended way for a reason, which we'll get to at the end of the slide. Okay, well, this brings up a question, which is, if you just hand me an arbitrary region in the table space, or really anywhere in Rn, and then I transform it somehow, in this case under G, and then I say, okay, well, what's the measure of that? How do you compute such a thing? Well, we go back to Calc 3. We remember our Calc 3, and we go, yes, I know, in fact, how to compute the volume of a function applied to a region. And the way you do that is you look at the absolute value of the determinant of the Jacobian of the transformation, and then you integrate that over the region. And that allows you to calculate the measure of the region under the transformation. And we go, thank goodness we took Calc 3. Well, what does that mean here? Well, let's go back up to this equation here and combine it with this equation here. This is how you calculate such things. And so we say, okay, well, the measure of g of e, we know we want that to equal n factorial times the measure of e. But we can rewrite n factorial times the measure of e as simply integrating n factorial over e. And we know that this is equal to the integral of the absolute value of the determinant of the Jacobian of g integrated over e. But we actually know something more, because we go, well, wait a minute, this isn't for a particular e, this isn't for a particular region in the table space, this is for every measurable region in the table space. And so, in fact, we need this integral equation to hold not for a specific e, but for all of them. Well, if an integral equation holds for all regions, then really what that's telling you is that the integrands themselves have to be equal almost everywhere, in the Lebesgue sense. And you say, oh, okay, now we're getting somewhere, because I know that my first mapping failed, so I need to get a better one somehow. How am I going to do that? And the answer here is, well, if for nothing else, restrict your attention to mapping such that the absolute value of the determinant of the Jacobian equals n factorial. It's like, well, that kind of narrows it down, right? What kind of mappings do I know that do that? I go, well, I took linear algebra. I remember my linear algebra. And I go, wait, a linear mapping in linear algebra, when you look at a linear mapping, its Jacobian is the matrix that represents the linear mapping from Rn into Rn. And we know how to take determinants of matrices, and they're single numbers. They're not functions. They're just single numbers. And so maybe I should look at linear maps or affine maps or something like that. Maybe a linear map will suffice. Maybe I'm just overcomplicating it with these polynomials. But in fact, those don't work. No linear map or affine map works, in fact. And the reason why is it has to do with the counting of what are known as extremal points. So that's not going to work. So although multivariate calc saved us, it gave us a push in the right direction, our linear algebra was of absolutely no use. We cannot use an affine and thus a linear map. That just, it won't work. What do we need to find? Well, the reason why I wrote this the way I did up here was to show you that the things for which we're looking are related to this idea of measure-preserving maps from ergodic theory. What's a measure-preserving map? That's where the measure of the inverse of a region simply equals the measure of that region. And that's precisely this equation here, but it's relativized to the regions. So we're looking for something that does this, and it's not affine, it's not linear. Okay. So how do we do it? Well, fortunately, my co-author figured it out. So what did he figure out? He goes, look, what we want to do is we want to associate the relative area of regions in the table space with the magnitude of entries of vectors coming from the hypercube. That's what we need to do. I said, what? He says, look, I'm going to give you a vector from the hypercube, And here's how we're going to generate our table. Here's how we're going to generate our x's. I'm going to give you the u's. I'm going to describe how we get our x's. The kth component of t is determined by sliding a hyperplane along the kth dimension of t until UK% of the remaining measure has been covered. Okay, so that's what it is verbally. So what is it geometrically? He says, well, look, here's an example. Let's start easy. We're going to go into R2, and we're going to sample from the unit square. And so we're going to get some vector out of there, say 0.874 and 0.236. And he goes, look, here's what we're going to do. The table space in R2 looks like a triangle. And so we're going to start at 0, and we're just going to slide this vertical line across the triangle. And we're going to keep sliding it until we have traversed 87.4% of the area of the triangle. So until the volume of this region, the relative volume of this region is 0.874. Because obviously the volume of the whole region is just 1/2. The relative volume of the region is 0.874. We're going to slide the vertical line until the relative volume of this region is 0.874. And then, once we've gotten there, we now have this line segment here in the triangle. And what we're going to do is we're going to start at 0, and we're going to walk up this line segment until we have traversed a relative length, not an actual length, but a relative length. This line segment has some amount of length. We're going to walk up it until we've traversed 23.6% of this line segment. This point here in the unit triangle is going to be our x1 and x2. So it's not a formula. There's no algebraic way of saying that, but that's what we're going to do. We're going to take a vertical line, we're going to slide it until we've traversed 87.4% of the area, and then we're going to walk up that line until we have traversed 23.6% of the line. All well and good, Mahoney. What do we do in R3? He goes, no problem. In R3, here's what we're going to do. We're going to grab a triple from the hypercube. So here's one, 0.488, 0.847, 0.236. Obviously, these are the two numbers from the last one. Well, what are we going to do now? Well, again, what is the table space in R3? It's a tetrahedron. And Mahoney says we're going to do the same thing, but instead of going area to length, we're going to go volume to area to length. So we're going to start at 0, and we're going to take a plane, and we're going to slice through the tetrahedron, and we're just going to start moving that plane. How far do we move it? We move it until the relative area of the tetrahedron here is 48.8% of the whole tetrahedron. We're going to move that plane until the relative volume traversed is 48.8%. Once we've done that, we now, because we have a plane slicing through the tetrahedron, that gives us a triangle. So we take a vertical line, we put it at the start of that triangle, we start moving that vertical line until the area traversed by that vertical line is 87.4% of the area of that triangle. That gives us a vertical line, and then we walk up 23.6% of that line. And that gives us a point in the table space, and those are going to be the probabilities we associate with this vector from the hypercube. Okay, so now we at least understand it verbally. We know what we need mathematically. We know what we need geometrically. And so we take his intuition, we take those drawings, and we say, okay, what is this? Well, because we're making statements about relative volumes and relative areas and relative lengths, how do we describe things like length and volume and area and whatnot? Those are integrals. So the geometric reasoning gives rise to some integral equations. And when you solve those integral equations, you get something that looks like this. And when you get something that looks like this, you say, I wouldn't have expected that, which is why I also didn't start the presentation with this. And you go through the same process you went through with the last mapping. You go, I was fooled once, so I'm feeling kind of fragile. But no, lo and behold, look, this is also a homeomorphism. It's bijective. What does that mean? It means that it's one-to-one. Different points in the hypercube get mapped to different probability tables in the table space. Every probability in every table in the table space has an associated point in the hypercube. The mapping is continuous both ways, so it's a homeomorphism. This is great. Again, though, you go, I've been here before. I've been hurt before. But when you do the calculations, lo and behold, the absolute value of the determinant of the Jacobian is exactly what it needs to be. Thus, regions of relative volume in each are preserved. On to intermission 2. When you are doing constrained optimization, one of the things that makes it work is the idea of the Lagrangian. And what does the Lagrangian do? Is that you have a function you're trying to optimize, and then you have these constraints that you want to have hold. Well, every constraint that you want to have hold gives rise to another variable in the Lagrangian. And the computation time increases with every variable. Therefore, it behooves you, if at all possible, to know how to somehow map all of Rn into your feasible region for your constrained optimization. Because if you can do that, you can dispense with the Lagrangian, which means that you only have the number of variables in your optimization which are in your objective function. And so the more maps you know that take Rn into specific areas, the better you are. The Mahoney mapping is an example of such a map. So for instance, suppose you have n discounts, but you don't want their total to exceed 50%. So what would your constrained optimization look like? It would look like some objective function subject to, I don't want the sum of these guys to be bigger than 0.5. Okay, well, how would you do that? Well, again, let F be the Mahoney mapping, because he figured out how to take the hypercube into the table space, but the table space geometrically is just the set of vectors who sum to less than 1. Well, here's what you can do. You can take all of Rn and you can map it into the hypercube simply using the logistic function, and then you can map the hypercube into the table space, and then you can just multiply the result by 0.5. And that allows you to map all of Rn into the feasible region. Then the inverse map looks like that. And then you can proceed with a direct optimization instead of a constrained one. All right, back to our regular scheduled programming. So now that we have a way to transform the hypercube into the table space, now that we have a way to parameterize in some reasonable fashion all probability tables, let's apply this to, say, the United States Census and see what happens. So again, let's remind ourselves of the sampling scheme. We're going to generate stuff from the hypercube. We're going to map it to the table space. This is going to give rise to a probability table with n+1 cells. We are then going to sample from the table, and then we're just going to look and see if a disparity occurred. And we're going to do that 5 million times. And that's going to allow us to estimate the probability of a disparity in the absence of bias. So this is a false positive calculation here. In the absence of bias with a probability of 0.95. Now, in case you're wondering, did I correctly implement the routine here here are a few checks for you. If you did, what you can do is you can actually figure out the distribution of each of the components in your table space, in your probability table. And their distribution is simply, looks like this for the first component. Easy enough to derive. What you can also derive is that it can be shown that the density for the vector in your table space is just n factorial. But that's exactly what you would expect. Since the volume of the table space is 1 over n factorial, if regions of the table space are equally likely, then you would expect the density to simply be a constant. Well, since it has to integrate to 1, the only constant it can be is n factorial. Lo and behold, it is. And then because you wind up with n plus 1 cells, what's the expected value in each cell? The answer, of course, is 1 over n plus 1. But also, since the density is constant and the table space is symmetric, actually, in fact, all variables have this same distribution. They're not independent, since we know that they can't sum to more than 1, but they are identically distributed. And so then if you're concerned to make sure that you have implemented the sampling scheme correctly, you can take a look at the values that you're generating and say use a Kolmogorov-Smirnov test and test it against this particular distribution here. Okay, so what's going on in the 2020 census? Well, it asks for a few things. It asks for the sex of the person. It gives 2 options, male and female. It asks for the Hispanic origin. It gives 5 options. It asks for race. It gives 15 options. In fact, it's even more complicated. The race question allows multiple answers. But for simplicity, for illustration purposes, we're just going to assume that only one answer is given. And although it does not ask for sexual orientation, because sexual orientation is such a big part of the public discourse, I thought it would be useful for illustrative purposes to include it. 2 options, straight and gay. So what does this give us? Well, this gives us 4 categorical variables taking 2, 5, 15, and 2 values respectively. And now we can do exactly what we said. We are going to generate tables with 300 values, 300 cells. We're going to select a sample faithfully, no bias. We're going to faithfully select a sample of size 100 from them, and we're going to look for disparities. Well, when you do that, what you find is that applying the scheme yields a probability of disparity in the absence of bias in the interval 0.996 to 0.998 with a probability of 0.95. If you're interested in what it looks like for individual variables, half the time, one of the values of one of the variables is going to be out of whack. It's going to be too big, it's going to be too small. 92% of the time, there's going to be some intersection of 2 variables. Some pair of values is going to be too big or too small. 97% of the time, 98% of the time, some triple of variables is going to, one of the triples is going to be too big and too small, and 95% of the time, same thing will hold for all four variables simultaneously. So what do we conclude? We conclude that if you're looking for a disparity and you're looking at relatively modest variables, if your sample size is 100, you're almost guaranteed to find it. So, what are the summary and implications? Well, again, we took a particular definition of disparity here, which is a univariate disparity at the 0.95 level for one of the values of one of the combinations of the various categorical variables. Again, you can take any definition of disparity you like. All of this framework will still work. I selected the one I did based on what appeared to be the implicit rule in the public discourse. Now, I know what you might be thinking. You might be thinking, but what about the Glavenko-Cantelli theorem? that says that as the sample size from any probability table increases, the probability of disparity's got to go to 0, right? Yes, that's true. That's absolutely true, that as n goes to infinity, asymptotically, the probability of disparity from a faithful sampling goes to 0. What we have shown numerically is that between 1 and infinity, there is the possibility of great variation. And thus, this particular intellectual apparatus is meant to be used as a first layer of an investigation of bias and perhaps its amelioration. So before proceeding to claims of bias, the first thing you should do is you should check to make sure that your definition of disparity is not overly sensitive as it was in this case. You should have a very clear idea of what your definition is and how big your sample size is going to be, and judiciously select your definition of disparity so that it's not almost guaranteed to happen as it was in this case. However, even if after you do that, you still see disparity, it is instructive to consider if the disparity is volitional, that is to say, someone is making a decision about it, or if it emanates from another source. And this is the idea of control variables. So what is a control variable? A control variable is what you think has to do with the phenomenon in question. So we opened this talk by looking at two different articles. One had to do with incarceration, and one had to do with being an executive in the C-suite. And while they referenced race and gender, if I pulled you aside completely out of this context, if I pulled you aside and said, hey, what does it take to become a C-suite executive? You would probably give me a list of 10 things or something like that. So, well, you got to be educated and you got to have this much experience and you got to be in this industry and this and that and the other thing. You would give me a bunch of variables. You would give me a list of 10 things. Those 10 things are the control variables because you have just admitted to me, hey, I think this also might influence the phenomenon in question. This might have explanatory power with respect to the phenomena in question. So, if you detect disparity, even after using the tools of this presentation, it's worth to considering whether or not it comes from volition, which would be the bias part, or from another source. On the mathematical front, you might say, I wonder if we can do one even better. Because I know the Hahn-Mazurkiewicz theorem, I know about space-filling curves. And I know that I can map the unit interval onto the hypercube. And you've given me a map from the hypercube into the table space. So maybe I don't even need to randomly select from the hypercube. I can simply randomly select a single random number and generate a probability table. And the answer is, yes, you can. However, that mapping from the unit interval into the hypercube is not a homeomorphism. The easiest way to see that is an argument by contradiction. If it was, what that would mean then is that the map from the hypercube back into the unit interval is also a homeomorphism, which means it's continuous. Which means that if we consider the restriction of that map to the hypercube minus a point, that's still continuous. But when you remove a point from the hypercube, that also implies the removal of a point from the unit interval. And thus you would be mapping a connected space into a disconnected space. So we can't get simpler than that. The other thing to observe is that geometrically there's nothing interesting about the table space. It's just a region in Rn. It's simply a region in the hypercube. Therefore, The reasoning applied by Mahoney need not be restricted to the table space, and in fact might be generalized to measurable subsets of product spaces. If this idea is chased out, what that might mean is that it's possible to get maps from the hypercube into much more complex regions in some canonical fashion. And what that means then is it's possible to get maps from all of Rn into these much more complex regions in a canonical fashion, which would greatly save time when doing constrained optimization problems. Finally, the gap between the intuitive and precise understanding of what is random has at least partially been bridged. I hope you found this presentation to be interesting and useful.